Hello everyone, and welcome to this video on a uniform plank on static equilibrium. And I think this is a really good question that illustrates an important point that, again, is very often not very well understood by students. So this question says, a uniform plank AB of length W and weight W rests with an end A on rough horizontal ground and the end B leaning against a smooth vertical wall. Right, let's have a sketch of our situation. Okay, so we have A, we have B. It is length L, and weight W. Okay, so we've got a weight of W newtons. We've got an angle here, theta, and here is also theta. Just get our sketch. We're going to have a normal reaction from the wall. I'll call that S. And we're going to have a reaction from the floor, which I will call R. A technician of weight 9W stands at the top end of B. So we've got our technician. And there's a technician with a weight of 9W up there. Okay, to prevent the plank from slipping, a colleague applies a horizontal force F at point A. So there's a colleague down here applying horizontal force F directed towards the wall. The force acts in a direction perpendicular to the wall. The plank is in equilibrium in a vertical plane at an angle of theta, where tan theta is equal to √3. So essential to get our little triangle. So we've got theta here. Now tan is opposite over adjacent, so √3/1, which means that the hypotenuse is going to be 3 add 1 square rooted, so 4, the square root of 4, so 2. From this, we can find out that sine theta is going to equal √3/2, and that cos theta is going to be 1/2. So those are going to be useful to us. Okay, perfect. The coefficient of friction between the ground and the plank is 1/5. Okay, so mu is equal to 1/5. The technician is treated as a particle and the plank is initially modeled as a uniform rod. Okay, determine in terms of W the normal reaction force from the wall at the point B. Okay, so what we're going to do here is, well, if we want to find this reaction here at B, then it would be really helpful to us to basically eliminate F and R there. So in order to do that, we should take moments about the point A. Okay, so I'm going to write down moments about A. And the reason we've done that is to eliminate these forces, because we're going to get an expression then that's just in terms of S. I should point out up here that this angle is also theta, because they are alternate angles. Okay, so taking moments then about S, what have we got? Well, we've got our technician who's all the way up there. Now let's think about our technician as well. So we've got a component of the weight of the technician as well. So the component of the weight of the technician that is perpendicular to the rod is going to therefore be 9W times by cos theta. So 9W times by cos theta, and that's times by the length of the rod, which is L. And it's cos because in this little triangle here, that side's the adjacent and that's the opposite. And there, 9W is the hypotenuse. So it's going to be 9W cos theta to get the component that's perpendicular. And a moment is the perpendicular component of the force times by the length. So the anti-clockwise, that's going to be a clockwise turning moment. So clockwise turning moment is going to be 9W cos theta times L. There'll also be a clockwise turning moment from the weight of the plank, which is going to be W cos theta, again, because that's the adjacent, that's the opposite, and we want this component here, and that's going to be times by L/2. So we're going to have W cos theta times by L/2. So those are our clockwise moments. Now, what's our anti-clockwise moment? our anti-clockwise moment is going to be coming from the reaction force, and that is going to be S sine theta. So this side here is the opposite. So we want S times by sine theta. And that's times by the distance, which is L as well. So we've got our first equation there, and this is perfect because when we substitute everything in here, we're going to be able to find out what S is. So that is going to be S sine theta times by L. Perfect. Well, L is common to all of these terms, so we can cancel out L. We also know that cos theta is a half, so we're going to have 9W times by a half plus W times by a half is equal to S times by root 3 over 2, because sine theta is root 3 over 2. So we can now combine these two together and see what we get. Let's just have a quick look at that. Let's just quickly see that everything's looking good there. Yes, so we've got L over 2 here. Actually, this one, cos is a half, and we've got L over 2, so that is going to be a quarter there. So we're going to have now our 9 over 2 plus a quarter is going to be 19 over 4. So that gives us 19W over 4 when we combine that one and that one is equal to S root 3 over 2. And then we can just rearrange this now in order to make S the subject. So S is going to equal 19W over 4 times by 2 over root 3. So that's going to give us that S is equal to 19W over 2 root 3. There we go. So S is 19W over 2 root 3, and we've got our force there. Okay, perfect. Right, that's part A done for, I think it's saying 5 marks. Now, part B. Find, in terms of W, the possible range of values for the horizontal force F that ensures that the plank remains in equilibrium. Okay. All right, well, first of all, let's resolve vertically, because we're going to need to know what F is. And in order to know what F is, we're invariably going to need to know what R is. Okay. So let's resolve vertically so we can get some kind of an expression for F. So if I resolve vertically, what I've got is the weight of the technician and the ladder acting down. So that's going to be W plus 9W. And I've got the reaction force here at the floor going up. So I have that R is equal to 10W. We also told in the question that the coefficient of friction between the ground and the plank is a fifth. So F is equal to 1/5 times by 10W. So F is equal to 2W. Okay, perfect. Right, so we've now resolved vertically to find R, and as a result of finding R, in turn, we've now found F. So it's now time to resolve horizontally. So let's now resolve horizontally and see what we get. So when I resolve horizontally, we have got, now this is a good point. So let's think about what's going on here. I've called that force there F. Actually, I should call it, I'm going to call it something different. Let's call it P. Okay, now this is a crucial point. So the this technician's assistant or colleague or whatever it is basically pushing, is footing the ladder essentially. So they're applying a horizontal force in order to stop the uniform plank from slipping. So they're applying this force, and it's just enough to stop the plank from slipping. So that means that the plank is on the point of going down the wall. Okay. So therefore, friction is acting in the opposite direction to which the plank is about to move. So friction is acting towards the wall, okay? Because basically, the plank's about to move down like that, so the friction is acting that way. So let's, resolving horizontally, what do we have then? We have that P plus F is equal to the normal reaction from the wall. So P plus F is equal to S. So that is super important, okay? Now, there's another alternative here that we should also need to consider, and that's what if down here on the ground, the colleague is applying a greater horizontal force, okay? So if there's a horizontal force is increased, then the plank is still in equilibrium, but it's now on the point of being pushed up the wall. And because this greater force is on the point of pushing it up the wall, that means that this horizontal force here has reverse direction, okay? So in that situation, what we've got is this. We've got our technician up there, we've got the colleague down here, we've got the horizontal force P, but now the friction is going the opposite direction because the plank is about to move up the wall, so the friction is now reverse direction, okay? So what we've now got when we resolve horizontally in this situation is that we've got that P minus F is equal to the S up there. So slightly different, yeah? So we could say that the P is equal to S plus F when we rearrange that. And in this one, we could say that P is equal to S minus F. Now that is such an important point and it's so subtle. So let me just re-emphasize that for in the sake of clarity. In this whole situation, this uniform plank remains in equilibrium. In the first scenario, a horizontal force is applied that is just sufficient to stop the plank from sliding down the wall, okay? And because friction acts in the opposite direction to which the plank's about to move, the plank's going to slide down the wall, so friction will be acting towards the wall. That's this scenario. So P add F equals S. P add F equals S. But in this alternative situation, the plank's still in equilibrium, the horizontal force has been increased, and the plank's now on the point of being pushed up the wall. So as it's about to go up the wall, the friction is acting in the opposite direction to which the plank is moving or is about to move. So in other words, it's now reversed direction. Okay, so we now have in this situation P minus F is equal to this reaction force S. Okay, and that is the whole, nothing's moved except that this force has increased and the friction has reversed direction. And that really is the crux of this particular part of the question. Okay, all right, so let's have a look and see what we've got here. So we have got that P in this first scenario is equal to S minus F. Well, we found out earlier that the S is 19W over 2 root 3. So S is 19W over 2 root 3. And that is minus our F, which we worked out to be 2W. This scenario here, we've got S, which again is our 19W over 2 root 3. And we have got plus F, which is 2W. So the range of values that we can have for the horizontal force P is that it needs to be less than or equal to 19W over 2 root 3 plus 2W, but greater than or equal to 19W over 2 root 3 minus 2W. And that's the range of values of P that we can have in order for the plank to remain in equilibrium. Super important idea, very, which is one of the main reasons I want to look at this question, because it's such an important idea. Okay, now part C, it says explain how the assumption that a uniform plank has been used in your calculations. Well, that's just that we're assuming that the center, the weight is acting at the center of the plank. So because it's a uniform plank, we're assuming that the weight is acting halfway, in other words, L over 2. So that's how we've used that assumption. Okay. In reality, the plank is designed to be thicker and heavier at the base. And I think this is presumably to stop the plank from slipping so much. Okay. The model is adjusted so that the center of mass is located closer to the end of A. State with reasons how this will change effects the magnitude of the normal reaction at the wall and the range of values of F for which the which the plank is now in equilibrium. Okay, so what we're saying in this next bit is we're saying, let's imagine it's not a uniform plank anymore. And let's imagine that, in fact, the center of mass of the plank has moved and it's not there, it's now down here, lower, closer towards the floor. Okay, so our W newtons is no longer there, it's down here now. Well, let's look. This is the equation that we had from when we took moments, okay, earlier in the question. And let's examine each of these components in turn and see what that will mean. This component is the technician, okay? The technician is at the top of the plank, okay? So we've got 9W cos theta times L. Nothing has changed in that one. The technician's still up there, so the distance is L. The angle's the same. The weight of the technician's the same. That one is unchanged. This is the turning moment that's due to the component of the weight. Now, in this one, that's the same, but this has reduced, okay? So that one is the same, that one is equal. This one has gone down, okay? Now, we have got an equation here. So let's have a look and see what's going on with this one. So we have got, let's just have a quick look at this. Okay. So let's just have a little think about this. So we've got an equation here. So everything has to remain in equilibrium. So if this has gone down, then that means that this force must also go down by the same amount. Because in order for it to be an equation, if you imagine, you know, if we've got a pair of scales, like some kind of, here's my crude drawing of a pair of scales, and we suddenly take a weight off one side of the scales, okay, in order for the scale to remain in equilibrium, we need to take the same weight off the other side of the scales, yeah, so that the whole thing remains in equilibrium. So what we're saying is that here, this component has reduced because the distance L is now less. It's not L over 2 anymore, it's less, so that's gone down. So that means that that can't change, the angle can't change, the length of the ladder can't change. So the only thing that can change is that S must also go down. So what they would want you to do is, by examining this kind of discussion here, you would need to say that the reaction force will decrease. So reaction force S will decrease. Okay, so the reaction force S will decrease. That's the first part done. Now the last bit, the range of values that allow it to remain in equilibrium. So let's come back to what we had before. This was our expression for the range of values that allowed the whole thing to stay in equilibrium. Okay, and what have we got? We've now got that the force is reduced. Let's just think about this. Let's see what we've got. Okay, so I think we're going to end up with a narrower range of values that are going to allow the whole thing to be in equilibrium. Okay, it's going to definitely be a narrower range of values, yes, because what we've got in our equation here is that this is P is equal to S minus F, and we're saying that this force here is actually now going to be smaller, and this force is S add F. So if we just write that slightly into different format that we had from a moment ago, so we've got this one is S minus F, and this one is S plus F there. So this has reduced and this has reduced. So it has the effect of narrowing the range of values for which the ladder would remain in equilibrium, because that force has gone down and that force has gone down. So it closes it in. Okay, so we can now say that the ladder will only remain in equilibrium for a narrower range of values. And that's the answer to that last bit. Okay, I hope that you found that helpful, and I will see you in the next video.